All right. We are here. It is officially the middle of the week-ish, the middle 3 days of the week. I'm not looking forward to the middle of the week, so I can look forward to the end of the week. How's everyone else doing? Yep. So we have an assignment that is due tomorrow. I'm hoping to see people in office hours after class with questions. I will be revealing the next assignment. I may even want to do that something like today so that we have time to get that in before next week's exam on Friday. So we'll probably have to do something very similar to what we did for the first exam for this assignment, which is if you submit it a little bit early, I can guarantee that you get feedback. If you submit it at the normal time, then it'll count, but I can't guarantee we'll get as much turned around as we can before the exam. Other questions about class or where we are? I guess by Friday you'll get a study guide. All right, we'll dive into it. Last time we were looking at the context-free pumping lemma, which was a little different from the regular language pumping lemma. We were using recursion and grammar instead of loops within state machines to prove this. So we're looking for a non-terminal that via some sequence of productions can derive itself. Our first example for this was showing that a to the n, b to the n, c to the n is not context-free. And we were able to pick a to the n, b to the n, c to the m for that, where we said that instead of representing the number of states in the DFA, m was the number of productions in the grammar. And as long as there's only ever a single non-terminal in each of those productions, then we can show that if each production is generating another new non-terminal, then the most we can see in a production, or the most productions we can see before we hit that recursion, is the number of productions in the grammar for very similar reasons to the loops, the number of states before we have to have gone back to a state that we've seen before. We can derive new non-terminals for each production until we reach the number of productions in the grammar. And if the grammar is capable of producing a language with infinite strings, then it needs to recurse on itself somewhere. So where does that come from? Where do we recurse back using some non-terminal that we've seen before, sometime before we reach the number of productions in the grammar? We also said that we can't assume that this is coming at the beginning of the string, since we can recurse in the middle, we don't know how much of the string is generated from that recursion. So we can't say anything about the first m characters or anything of the sort. We just know that a single instance of that recursion will produce at most the number of characters that represent now the number of productions in the grammar. So because of that, we can use that recursion to show this. So we said that this will break down into 5 cases. We had this u, v, x, y, z, where u and z were the one-time parts of the string that are generated when we go from the start non-terminal until we get to that first non-terminal that is used as part of that recursion. Then v and y were the 2 pumped parts that represent the portion of the string that's generated when we recurse from that non-terminal to itself. And then x was the portion of the string that is generated when we go from the last iteration of that recursion to termination. So that's what each of those symbols stood for. So we're interested in vxy, the length of vxy, since we know that it's going to be less than or equal to m. So because of this, that's the reason we have exactly these 5 cases. We know the length of vxy has to be length less than or equal to m. So we can't have the case of some A's, some B's, and some C's, because that would eat more than m characters, because there are BM or MBs in the middle of the string. So the 5 cases were all A's. We can get all A's with length less than or equal to m, all B's, all C's, some A's and some B's, or some B's and some C's. And we found that regardless of the way that we tackled this, we either produced more A's or B's and C's in some way, shape, or form, and that broke the language definition. So because of that, we can prove that this language is not context-free. Were there questions on this first example and how that worked? All right, let's get another one. It's our old friend WW, which is in your homework to show that it is not regular, but in fact, it's also not context-free. Any intuition for why this might not be context-free? Remember that WWR was context-free. Maybe that helps.
It's not how a stack works.
Yeah.
You can't off the bottom character of a stack.
Yeah, so if we were carrying along a different data structure rather than a stack, we could recognize this. What data structure would we need to carry along with us?
Something like the link list or even an array that change.
Yeah, anything that can be a queue. We want a queue to recognize this. If we're reading W from front to back, then when we dequeued from that, we'd be dequeuing from front to back, and we could map using non-determinism wherever the middle of the string happens to be. You would fork at every possible character and say, is this the middle? All right, I'm gonna duplicate my queue, and I'm going to now I'm gonna check using non-determinism. I'm gonna check whether this is actually the middle of a string. If not, then I'm gonna enqueue it and continue moving, and you'd use non-determinism to be able to figure that out. But since we only have a stack, we can't do that. So let's see how that proof looks when we are looking at this. So always the first question, what is a good string to pick for this? I want to pause for a second because this is one of the big challenges when it comes to anything pumping lemma is picking a good string. Any ideas for what we could use?
Like A, B, A, power of N, B, power of N.
I love it. Exactly what I have. So we're going to utilize something that we already know is either context-free or not context-free. But why is this a good string to pick? What is the intuition for how this string is going to help us prove that this language is not context-free?
Assume there's an equal number of A's and B's on both ends.
Yeah, that we have to have the sum of the number of A's and B's in W is the same as the second case of W. So if we are going to try to show this, there are some cases again. We need a sliding window of length M. Where could that sliding window be? It could be in all A's, it could be in some A's and B's, it could be in all B's, it could be some B's and some A's. Before we get back to all A's and all B's or A's and B's from the second part of the string. There's that extra consideration though of some B's and some A's in here that was not present before. So it could be A's and B's, B's, B's and A's. And then we're back to repeats of what we've seen before. So that's what we need to handle to be able to show this. Again, thinking about this kind of like a game. Just what are all the possible breakdowns of VXY? And so any of those would be possibilities for what that breakdown could look like. So they're all breakdowns that we need to be able to handle. So again, to prove it's not context-free, we find an I for each of those cases that says when we pump it that many times, we get some string that's not in the language. Is there a value of I that would work regardless? You can almost pick anything here.
And let's go with I equals 2 just to be consistent.
Yeah, you could say I equals 2. The way that I'm going to continue is with I equals 0, but I just want to demonstrate what it's like when you're taking it away rather than adding it. But you could absolutely use I equals 2 here and it would work flawless. So the intuition behind this is if we see a VXY that is all A's, if you take out at least one A from the first segment, then we don't have the same number of A's in the first segment and the third segment of this, A to the M and A to the M. WW means that we need a perfect match. So if you're making a change to the first W and not that exact same change to the second W, then it's not the string WW. It's not a repeat of itself anymore. So you can make an intuitive argument that the resulting string is not in the language because we don't have the same number of A's here as here. We're taking away between 1 and M A's from here. No way this is the same. We're taking away 1 or more A's from here. These aren't the same. So that's the way you're going to handle that particular case. If we have all B's, then you just use the second part and the fourth part. If we take out at least one B from here, we don't have the same number of B's since these M's need to be equal to each other in WW in order for that to be the case. Then we've pumped in a way that's anti-pumped, taken away the one recursion that was used to produce this string. If we take out A's and B's together from the first half or the second half, then we can just state that there are differences in A's and differences in B's between the first instance of W and the second instance of W, so they cannot be the same string. Final case, if we have some B's and then A's, we end up with a different number of A's between the first and third segment because the overlap for this was between these two. So if we're moving at least one from here, those aren't the same. If we're moving at least one from here, then those aren't the same. So it ends up being almost the same argument across the board, but you just have to show here are all the cases, here are all the possibilities that we could pick for the breakdown of VXY. Once we look at all of those, we pick an I for each of them, and it doesn't really matter which I you pick. To give you a sense of what this might look like visually, here's our string A to the M, B to the M, A to the M, B to the M. We know that VXY has to be less than or equal to M characters. So this would be stating that in the grammar that derives this string, as we move to get to the recursion, this is what's produced in the front, and this is what's produced at the rear, all of that. And that's just getting to the recursion. When we recurse, going from the non-terminal that recurses back to itself, it's going to produce this B and this Y. And then once we have that portion of the string going from that non-terminal to termination, we'll produce the X, whatever is remaining there. And that generates this entire string. So we're arguing that there is some grammar that does this in some capacity. Somewhere where this VXY has to be a length less than or equal to M, somewhere along this, that grammar exists. And we are proving by contradiction that grammar cannot exist. Because if it did, then there would be some place to put this VXY, where if we took out the V and the Y, we would end up making some change to this first half of the string that we are not making to the second half of the string. And because of that, we can't have two successive strings of the same type, the same set of characters. So we're just breaking this down into cases. Where are that V and Y coming from? Are they coming from this chunk of A's, this chunk of B's, some overlap of A's and B's, and you can see that V here is all A's and Y here is all B's. But regardless, we know that the length of VY has to be at least 1. If it could be 0, this would be really difficult to do, but since it has to be at least 1, now we know that we're making some change to this string and we're not making to this string. Therefore, it can't stay in the language, no matter where you put that VXY. Questions on example 2, how that works? Let's look at another one. A to the n factorial. Can we show that A to the n factorial is not context free? let's start with, what's a good choice for the string based on this?
Just go m factorial to start.
Yeah, there's not really anything else we can attach ourselves to, right? We know that the string we pick has to be in the language. So we have to pick something that is a to the n factorial for some n. So let's pick m, the number of productions in the grammar, and so we can say a to the m factorial is going to be the string that we attach ourselves to. Any thoughts about how we could proceed with this? How would we be able to show this is not context-free? What's the next factorial past a to the m factorial?
E to the m plus 1 factor.
A to the m plus 1 factorial. Let's draw this a little bit. We have a to the m plus 1 factorial. How does this differ from that? If we were to write this in terms of that, how could we do it? Think maybe how you learned induction. How could we write a to the m plus 1 factorial in terms of a to the m factorial? Basically, we want to say, we want an expression in terms of a to the m factorial. What can we add to this that makes it equivalent?
1 plus
A plus a new factorial.
A single a? A good start. How many more a's? Let's say, I don't know, m is 10. If we can instantiate it, maybe we can see what's the difference between 10 factorial a's and 11 factorial a's.
Do you do this as a in factorial times a?
I'll even do this with a smaller value. Let's say we have 3 factorial and 4 factorial. If we're writing 4 factorial, what is the expression? 4 times 3 times 2 times 1. Writing this in terms of 3 factorial, what is it? It's 4 times 3 factorial. This is now just this value of m plus 1.
Oh, it's a to the m plus 1.
Yeah. A to the m plus 1 times, or concatenated with a to the m factorial. So this is going to be incredibly important for coming up with this problem, because how many a's do we need now in order to get to the next factorial? More than m. How many a's can vxy represent? At most m. So that's what's going to be the key insight allowing us to make this connection. Does that intuitively make sense? Maybe? Ish. So we now have the old a to the m factorial. So if we're pumping vxy to try to hit a to the m plus 1 factorial, we need to generate an extra m plus 1 a's in order to get there. If we say the length of vy is between 1 and m, then this says that we're going to be adding, if we set I equal to 2, we're adding at most m a's to this. So the length of y, not y, the length of vy in this case is between 1 and m. So if that means the length of y, length of this, let's say the length of vy is 1, length of vy is 2, all the way down to the length of vy is m. If we set I equals 2, how many characters are we adding when we recurse this that extra 1 time?
n+1 every single time.
We're gonna produce an extra 1 A, an extra 2 A's, all the way down to an extra M A's. Right, does that make sense? I think, maybe, this is the important part. These are all of the possible lengths of Vy. This is when we set I equal to 2, how many more A's we're going to be adding to this string. If we need to produce m+1 A's in order to reach the next factorial, can we do that? No, we cannot do that. The number of A's we can add is at most m. So we cannot reach that m+1 that we need in order to state that we got to the next factorial. So this value of I says that for any actual value for the length of Vy, we're not producing enough A's to get to the next factorial. So if we wanted to show this algebraically, I'm trying to do this intuitively. Hopefully that's helping, but let's look at this algebraically now. We end up with the string without the length there. So we end up saying we're gonna end up being, I'm gonna get rid of this. We can look at the portion of the string that is length without everything, without, sorry, the recursive part of it. So U and X and Z. So we can state something like, all right, m factorial minus k plus L must be equal to some j factorial for some j, by definition. Since this grammar exists, if we take out everything except for the recursive part, we know k plus L is less than m because of the pumping lemma constraint, which I just showed. We are able to phrase this as an inequality that says that we can now take m factorial, we want to take out k plus L, these number of values that we came up with for the string uxz. So that's this length. This is the length of uxz has to be greater than m-1 factorial. You try to look at there's no factorial that works for. There is no j that satisfies that. But either one of these approaches is good enough for this class. If you want to take an intuitive approach, that's okay. If you want to take an algebraic approach, that's also okay. Just make sure that you're consistent, that the algebra and logic that you use are correct, and you're not making any assumptions that you can't make. Questions on example 3? Let's look at one more. A to the n, b to the j, such that n equals j squared. This is the biggest challenge problem here, I think. I wanted to give you one that looks very similar to what might be thrown on the challenge problem of a homework. Too hard for an exam, though. So what is a good choice for our string?
A, M, B.
You say A to the M, B to the M squared.
We want the exact reverse. Yeah,
Or A
so
to
we
the-
know that n equals
Oh,
j
okay.
squared. So that tells us that we want the square on the first term. But yeah, we're gonna use a to the m squared, b to the m. Why is that a good choice?
Should be. Should be on B and on A.
Should, what, sorry?
Should square be on A.
when we say that n is equal to j squared, then we need this value to be that value squared. We square this to get that. So. Am I wrong on that? No. No.
I mean, I guess it's just.
Yeah, so it is a little bit confusing. The square of that is this, m squared is that. How do we want to proceed?
String could either be all A's, all B's, or all A's, then all B's, right?
Yeah, so we have three cases here for what VXY could be, all A's, all B's, or some A's and some B's.
We either have to choose, even if we do the whole string, we can only have an even number of A's and B's if we generate that. If we factorial that, or we have
Yeah,
more A's.
the A's and the B's is easy. We add some A's to this, we've obviously broken the balance. The balance is very tight knit. We have to have exactly the square number of A's as we have B's. Add some A's, we're broken. Add some B's, we're broken. But what about some A's and some B's? Is there an alignment of A's and B's that would allow for us to pump that and produce a new square? Let's instantiate.
Not here.
And just try to take a look at this. Let's say we have 9 A's followed by 3 B's. Is there some overlap between here? What do we have to do to this string to be able to get to the next one? So this would say this is 3 squared and 3. So we would need 4 squared and 4.
Right, but with the grammar reductions, you can only curse that 9 and 3 in the middle, so you might start with the square, but then you can't.
Yeah, so we need this one recursion to generate 7 A's and 1 B. That length is 8, which is more than m. But it would be possible if you could overlap VXY with exactly 7 A's and 1 B to produce the next square.
Then you have to do that again, because 25. and
Right.
It's more,
Gonna be
you have to
different.
repeat that as well.
Yeah, the next one would be 9 and 1, 11 and 1, 13 and 1. Because have we seen that pattern before, that the squares are just a strange sequence of the sum of odd numbers?
Yeah.
1 is 1 squared, 1 plus 3 is 2 squared, 1 plus 3 plus 5 is 3 squared, 1 plus 3 plus 5 plus 7 is 4 squared.
It's the difference between squares grows linearly, but
Yeah, the difference between, but because it's a slope, then we can bring in calculus and say, then the integral of that's gonna be quadratic, which is why the area of that is quadratic. It all comes together. So this gives you a little bit of a hint as to where to go. Yeah.
Did you go to this refresh on where you got the 7 and 1 from again?
Yeah, that's the difference between when we went from 9 and 3 to 16 and 4,
Yeah.
this difference, we had to add 7 to 9 to get 16 and 1 to 3 to get 4.
Yeah.
So this would be the next square. So it's the difference between this and that is basically, if we found a VXY that was exactly aligned right there in the A's and B's, then we could recurse and generate that. But that was less than it, that was more than m to do that. Is there a value for this where it would be less than m? So what happens if we generate something like 100 as our starting power? 100 squared is 10,000. So we'd have a to the 10,000, b to the 100. What do we need to do to generate the next one? So this is going to be b to the 101. What is 101 squared?
10,201.
201. Sense. So we need to add here an extra 201 characters. M was 100, so we're getting a little bit closer. Now it's just twice the value. Is there any value for this where this next one is going to be less than M? Or greater than M? Is that something we could attach ourselves to as a potential proof? Be one way to tackle it. Let's take a look. So we know that there are three choices for the breakdown for VXY: all A's, all B's, and some A's and some B's. The all A's and all B's are going to be easy. Argument for some A's and some B's, a bit more difficult. So if V is made up of all A's and Y is made up of all B's, this means that potentially V and Y could grow at their respective rates that they need to generate the next square. If the length of V is 0, then we can just get rid of the Y and that will break the string. If the length of Y is 0, you again can do exactly the same thing. This would break down into the other case. So if B comes from, I guess I can use this. If B comes from here and Y comes from here, if either of these lengths is 0, then all we're doing is subtracting some B's or subtracting some A's, which is the same as these first two cases. Does that make sense? Because all we know is the length of BY has to be greater than 0. So B could be length 0 or Y could be length 0. They just can't both be length 0. So otherwise, we're in this case where neither the length of B nor the length of Y is 0. So we can do something that shows, all right, if we take M minus the length of Y and square it, and set that less than or equal to M minus 1 squared, what happens? Because we want to be able to find a way, is it possible to subtract some amount of Y here and get to M minus 1 squared? Can we do that? Algebraically, we just factor M squared minus 2M plus 1, which is directly less than M squared minus the length of V. And there's our counterproof. There's no way to map the square of Y to V. So that's the same thing of doing what I just did on the board, but now giving a general proof for why this will not work for any value. Any questions on that? I honestly myself prefer the intuitive version. That's what makes me a computer scientist and not a mathematician. How are we doing? Do we feel like we have an understanding of the process of the context-free pumping lemma? How do we feel about that, just in terms of where we are?
You actually algebraically know.
I think I get the idea.
Yeah, I see a lot of sideways thumbs, like we're all just about at that point, which means that, to me at least, the idea of what you need to do is clear, and we need practice to make sure that that cements and sticks. So that's what our next homework, actually, I'm not sure if it's the next, it might even be the homework after the next homework, but we'll eventually get to this and get some practice with it before we take an exam on it. Don't worry, it won't be on this next exam. I think we're past the point already of what's going to be on the next exam. I don't want to throw 2 different pumping lemmas on the exam. That'd be especially cruel. How do you design a 1-hour exam with 2 pumping lemmas? You don't. I feel like the pace of the class has been overall pretty fast, so I can take a little bit of time at some point and make up for that a little bit. Maybe we can come in with some more practice problems.
Maybe spend like a class to go over this.
Yeah, I'll figure out some way of coming up with some practice problems, and we'll come in and just go over some of the logic for that. So we were able to see a distinction between linear and nonlinear context-free grammars. This was the Greibach normal form that we used before to be able to say we can now linearly, we map this to the deterministic push-down automata. That language class is called linear languages. So if there's a linear context-free grammar, then there is the language is linear. So again, we have this interesting hierarchy of languages. I'll even draw out the first bit of Chomsky's hierarchy. We have regular languages. Outside of this, we have our deterministic context-free languages. Let's call them linear. And outside of this, we have context-free. So we see that we have each of these languages are some regular languages are context-free, but there are some context-free languages that aren't regular. Every regular language is linear, but there are some linear languages that aren't regular. So that's all is the same. Large Venn diagram. So if you can derive a nonlinear grammar for a language, it doesn't imply that it's not linear. This makes sense, right? You can write a context-free grammar for a regular language, but it doesn't mean that it's not regular just because you can make a context-free grammar for it. If we wanted to prove that a language is not linear, we'd need to prove that no grammar can exist for it, which means that we would need a third pumping lemma. I will not go into this in a level of detail that requires you to know this pumping lemma, but it's actually very similar to the context-free pumping lemma. One big difference, we could derive a pumping lemma for linear languages by saying, let that language be an infinite linear language. There exists some integer m such that any string that is in that language with the length of that string being greater than or equal to that m can be, again, decomposed into UVXYZ. We still know, except now instead of it being the length of VY, we need the length of UVYZ to be less than or equal to M. So what's generated before the recursion and the recursion has to be less than or equal to M. It's an interesting result. We also know the length of VY has to be greater than or equal to 1, such that, again, exactly the same thing. The difference is just that we have the U and the Z embedded in that length of this has to be less than or equal to M. And this tells us, very interestingly, that the recursion has to happen within M characters at the start or the end of the string. So as we move inwards from the string, we have to hit that recursion within the first M characters of one or the other of those. It can't be so embedded in the middle of the string that we can't get there easily. And that is the difference between these two classes of languages. So if you can generate something like a deterministic pushdown automata, what that tells you is that the recursion for that must happen within M characters at the start or end of the string. Middle string can be arbitrary, and the logic for doing this is very much like the context-free pumping lemma. So this is not something that I'm requiring you to know. Moving forward, no homework questions, no exam questions on, I think we've all had enough of the pumping lemma already. We're ready for the cool part of the class. We start with the cool part of the class and then we hit this roadblock in the middle where we talk about pumping lemmas for way too long. And then we start talking about cool things again at the end of the quarter. So we're moving back to that point where you can stop hating your lives, at least with regards to this class. So I just have a few last thoughts here on context-free languages. Very short, just a couple of closure properties of them to make note of, because I think this is more interesting than the regular closure properties. So first and foremost, what can we do with context-free languages? This becomes very important for designing compilers. What can we actually state about multiple context-free languages and set operations on them? So what can we do? Context-free, so first of all, do we remember the definition for closure? Man, we could work on our discrete classes.
Everything that's in the universe, but not in the set that we're.
That would be a complement. So a closure says that under a particular operation, the result of that operation gives you something that is also within that set. So if context-free languages are closed under union, that would say something like, you take the union of a context-free language and a context-free language, and the result is another context-free language. You take for an intersection, you would say, if context-free languages are closed under intersection, then a context-free language, intersection context-free language is guaranteed to give you another context-free language. Any ideas about which set operations or thoughts on which set operations context-free languages are closed under? We know one of them. We proved one of them earlier. We proved union. How did we do it? We said that if there exists a grammar for a left-hand side of a union and a right-hand side of a union, then we could specify the new production, the new start non-terminal can be the left-hand side start non-terminal or the right-hand side start non-terminal. And that gave us a grammar for the entire union of two languages. So that would be how you would want to go prove that a context-free language is closed under union. The result of that union operation onto context-free languages gave you back a context-free language. They're also closed under concatenation. If you take a language and try to concatenate it such that any string in the first language followed by any string in the second language, could you state that that language is context-free? And the answer is yes. They're closed under star closure. So we have 0 or more repetitions of some language, and each of those will have an associated grammar or an associated NPDA. However, they're not closed under intersection. They're not closed under complement. There is one rule with intersection, and the reason I use this entire final thoughts couple of things is we can actually get and bypass the pumping lemma and a couple of side cases if we can recognize something. So if you intersect a context-free language and a regular language, the result is guaranteed to be a context-free language. But we couldn't state that if we took the intersection of a context-free language and a context-free language. That's kind of a counterintuitive result. But you can imagine just how difficult something like this is. That's supposed to be superscript. The language is a to the n, b to the n, such that n is greater than or equal to 0 and not equal to exactly 100. How in the world would you show this to be context-free? Would you want to write that grammar? Would you want to draw that NPDA? Question?
You could show that it's the intersect of the other things.
Yeah, you want to show that it's the intersect of context-free and regular. We've been able to show that a to the n, b to the n by itself is context-free. And something not exactly 100 times is regular. So if we took an actual concatenation, that's not an actual intersect of those two, we could just use that rule and the associated proof to show that the resulting language is also context-free. But thinking about what would it be like to make this grammar? How many rules would you need in order to structure this to be able to represent this language?
At least 100.
Yeah, we need something that says, all right, we can generate the first A and the B recurse in the middle, the second A and the B recurse in the middle. And you want to be able to terminate at any of those points. You couldn't just put them all together because what about AB? That works. What about AABB? That works. It's only exactly A to the 100, B to the 100 that we want to say no to. So we would need a bunch of productions to accept everything less than 100 with a different production for each one of those values. And then you'd need a general one for 101 or more. That is a massive grammar for no gain. The actual grammar for A to the N, B to the N was really simple. So as soon as you add one constraint to that, it can blow up the size of the grammar, blow up the size of the NPDA to a disgusting level. So to look at it, we just use this rule of, well, it's an intersection of a context-free language and a regular language. So the context-free language is A to the N, B to the N. And the regular language is W, or I guess A to the N, such that N is not equal to 100. Since both of those languages, one are context-free, one is regular, the intersection of that is guaranteed to be context-free. Proof done. So the real reason for this is that we can do something like this to bypass the pumping lemma. So let's say we wanted to look at this language. We wanted to show that all strings such that the total number of A's, number of B's, and number of C's are all equal to each other. What would that look like to use the pumping lemma? We could absolutely do that. Any thoughts on what we want to use for a string for that? It's actually really easy. We use the A to the N, B to the N, C to the N that we just had the example on, and that would, following exactly that same proof, would prove this. However, we can even bypass that by saying, let's take the intersection of this language and the language that is A star, B star, C star, which is regular. If we intersect these two languages, then we get the result being a context-free language. Great. Is that going to be the case? We need to show this by contradiction that that cannot work. The result of this has to be context-free. Is there any obvious, if we take the intersection of this language and A star, B star, C star, what is the result of that intersection? Yeah. We've already shown that that's not context-free, so we're done. Does that make sense why that works?
Because star codes is a universal set, and you didn't see the end, it's a subset inside.
Yeah, it's a subset such that all of them are equal to each other. Yeah, so we take that intersection and we say, well, if this language is context-free, then this language needs to be context-free. Since this language is not context-free, this language also cannot be context-free. Way simpler than doing the pumping lemma. So this is a tool you can absolutely use if you find the right place for it. Just the knowledge that the intersection of a context-free language and a regular language must be context-free. So if you can generate a language by that intersection of the language you're trying to look at and some regular language, get some intersection that gives you a language that you know is not context-free, then the result is that this can't be context-free either. And that's a much easier proof by contradiction than going through the entire pumping lemma. Yes, yeah, I'm reading your message, Kiva, that looks right. All right, so what can't context-free languages do? Now we're getting to that more exciting part of the course again. So I want to very quickly go over this and then we're gonna head out for the day, but we're transitioning into what are the weaknesses of context-free languages And what is the next language class outside of that that represents everything that we can write a program to solve? So there are some big issues with context-free languages. We don't know. We've never been able to show that an algorithm exists for determining whether two different context-free grammars generate the same language. A really simple problem. Easy to prove that they don't. Just find a counterexample, right? You just say that here's a string that one can produce, the other can't. But if you're struggling to find that example, when do you know that these two grammars generate the same language? Imagine writing a program that takes in two grammars and spits out yes or no, these represent the same language. Answering no is really easy. Eventually you find a counterexample, but answering yes requires you to iterate over an infinite number of strings. You will never be done with that process. Who says that you just haven't found that one string yet that means that they're different? You would never be able to answer that question. So that's going to motivate the study of everything else we do this quarter about theory of computability. Because if we can solve some of these problems, then the world becomes a scarier place, to be honest. All right, we'll come back tomorrow and tackle that. I'll start office hours now if anyone has questions on the current homework or anything else. You all look dead. Go get some sleep.